Hi there. Thanks for being with us today. My name is Carmina. I'll be your host for today's presentation, Everything High-Frequency Circuit Designers Need to Know About Stability Analysis. Okay, so let's adjust your screen a little bit because Matt will be sharing some slides and some demos. So when you have a chance, you want to make those screens a little bit bigger. It's pretty easy, just at the top right. And then we have a resource list. Matt has created a number of videos. We added some resources, and so you want to make sure you can find those. And then anytime you have a question, just submit them through the Q&A widget. And then remember to fill out, we'll have a short survey, and that's to the right of your slides, but I think it's over this way on since I'm facing you. But if you complete it, you can get a chance to win one of two $25 Amazon.com gift cards, and that's applicable for the live session only. So thanks for being here live, and it's not applicable for on-demand viewing, and we'll notify you within 72 hours. So our presenter today really doesn't need an introduction. A few years back, as I mentioned, he created the popular How to Design a Power Amplifier series on YouTube. And then earlier this year, he created his How to Design a Stable High-Frequency Amplifier playlist. When he isn't this busy, he likes to enjoy a nice pint of Pliny the Elder. But what's clear is that folks like Matt, he wants to make your work life better. He's here to help. He is our rock star. And with no further ado, Matt, welcome. You now have the floor.
Thank you, Carmina. All right, let's see. I should be able to switch this slide. Yeah, so today, as Carmina mentioned, there's a lot of different material out there. We've done a webcast about stability analysis. I have videos as well out there. So today I'm going to try to give you an overview, and I have a couple live demos which are new. I'm going to do them completely live. So there's some material in there you haven't seen before. So I'm going to give kind of an overview of the content that I have in the videos, and then we'll get to the live demos, hopefully with enough time to go through them. So as always, feel free to type questions in the chat. When we start out talking about stability analysis, at least if you're a high-frequency designer, the first place everyone tends to go is K-factor. And K-factors, I mean, it's a great metric. I've used it quite a bit in my own hardware design career. But you know, when you start digging into K-factor, there's a few issues with it. And I talk about these in a little more detail in my YouTube video. But the main issue I think that you'll run into with K-factor, at least as far as accuracy is concerned, is it's based on an assumption that was sort of an afterthought when it was originally written. This was this paper by Rowlett. This is a measurement technique. There wasn't much simulation stuff out there at the time. So the condition really was that stability factor is valid when the open network, or the ideally terminated network, which means terminated with an open and short, is stable by itself. And that is the assumption that underlies everything about K-factor. Back in the 1990s, I've got a paper here by Struble and Platzker, who were able to demonstrate a ring oscillator that has a super stable K-factor and yet was completely unstable, shown by their other metric, the normalized determinant function. So the problem with K-factor is you can't always rely on it. There's a few other issues there as well. So then engineers tend to want to look at different approaches to use for stability. And at least I can speak from personal experience. You know, the first time I started looking at all these different approaches, it seemed like this really tangled web of different techniques and things, and all of them seemed like they could be accurate in certain cases and maybe inaccurate in other cases. And I was just really left confused. So my hope with the videos and this webcast and everything else that I'm presenting is to try to help you untangle all of this and actually start using these things as tools and not just trying to figure out what they even mean. And what I'm going to show you is a capability that we've put into our design tool, Advanced Design System. And these things are called WS probes. They're named after their inventor, Tom Winslow, Dr. Tom Winslow. He's a technical fellow at MACOM. And he's developed this probe that essentially allows you to access all of these techniques from just one simulation. So some of what I'm going to do today is just show you the different techniques, how you use them, and then you can derive them all just based on post-processing using the probe. And again, this is a brief overview. I think I've got over an hour of content up on YouTube. I've got a 7-part series. And in fact, I just made a new video for the new release of ADS because there's a new technique in there. I'll talk about that today too. But if you want more information, this is going to be a little bit more high level. You can watch the YouTube series, you can pause it, you can rewind it. It's pretty extensive amount of technical information in there. Okay, so this is the agenda for today. We had the introduction. I'm going to go through a background, just talk a little bit about some of the basic concepts in stability. We'll talk about some common techniques. So we'll talk about loop gain. There's multiple ways to do loop gain. We'll talk about some of Bode's work, return ratio and driving point in minutes. And we'll talk about some modern implementations, normalized determinate network bifurcation. And then I'll introduce you to this probe, which allows you to really unify all of these techniques. And then hopefully I'm going to try to cover this in about 30 or 40 minutes, and then we'll have some time for the live demo. So I'm just going to show you how the probes work and go through a couple common things I've seen people run into. Okay, so before we get started, we have a poll question here. I've never done this before, so hopefully I can do this correctly. So the question is, why might k-factor sometimes prove inaccurate? Is it that it doesn't consider the network determinant? Is it that it's based on the assumption that the unloaded network is stable? Is it that simulations don't always have enough sweep points to determine if it goes below 1? Does it only apply to one stage amplifier or all of the above? So if you could take a minute to fill in the poll question. And then Carmina, am I allowed to, should I talk about the answer or should we wait? I don't know how this works.
You can talk about the answer. You can do whatever you want, Matt.
Oh, okay, I'm in charge. That's a first. Okay, so all right. Well, I'll give you a minute to think about it. And so all of these pieces, I'm actually going to walk through each of them. I think it's kind of interesting. The network determinant is actually a consideration in the stability factor. It's called the stability measure. It's another thing that you need to look at when you're considering the network determinant. The correct answer is that it's based on the assumption that the unloaded network is stable. The sweep points, yeah, if you don't have enough sweep points, you can certainly miss high Q oscillation. So I've seen that happen before, but it's not a problem with just K-factor. That can happen for anything. And it only applies to one stage of an amplifier. Actually, K-factor only applies to the external parts of an amplifier, so like the source and load terminations. All right, so there you go. All right, everybody, it looks like most people got the right answer. So that's, well, some people picked all of the above, which I can see. It was a little confusing, but those are the results. Cool. Okay, let's talk a little bit about what makes a system unstable. So, you can crack open your old college circuits textbook. Mine is Sedra and Smith, by the way, and I think I can find the page in Sedra and Smith. I've got it bookmarked now, where, stabilities and instabilities really arise from these gain feedback systems. This is the most basic view of instability. And essentially, we can take a look at a gain feedback system. We can derive a transfer function that looks really simply like what I'm showing here. And the bottom term, that AF term, is called the loop gain. So, of course, when the loop gain gets to be 1, the denominator goes to 0. The closed loop gain, the transfer function goes to infinity, and we have an oscillation. So that's kind of the simplified, most basic view of oscillation that we can get. Just want to dive into this a little more detail. I'm actually going to show you this in one of my demos later today. But the transfer function is really an S-domain equation, of course. And you may need to go back and recall that we can of course break these up into poles and zeros. We can decompose this type of a transfer function into numerator zeros and denominator poles. And if you look at the Laplace transform for this type of function, it comes into an exponential in the time domain. So the exponential in the time domain is really the key thing to make something oscillate. And it turns out that, if you have an exponential, of course, you can have a positive or negative signed exponential in the time domain. And it's good to have a negative signed exponential because these decay versus time. If you have one with a positive side, everybody knows they grow. So these things map to what's called the right half S-plane, and those produce growing exponentials. So if you're an amplifier designer, you do not want to be anywhere near the right half plane with your designs. Okay, so now I'm going to talk a little bit about loop gain here. How do you find loop gain? And I'm just going to do a really basic derivation because there's lots of ways to find loop gain, but in essence, you do something like this. First you divide the circuit, right? So we need an amplifier and a feedback block. And so I'm making the transistor the amplifier. And by definition, I think a lot of times people might think, well, these two components, the L and the C, are the feedback. But in reality, if you have a 2-block system and you're going to designate one block the amplifier, then everything else is the feedback, including, by the way, the input and output terminations here. So So from there, we break the loop somewhere between the amplifier and feedback, and we somehow stimulate one side of it, perhaps with a voltage, and we observe what comes back to the other side. And that thing that's returned through the other side is then the product of the input signal and the gain function and the feedback as well, which is the loop gain. And there's a couple of different ways to look at this. Probably the most common way to look at it, especially with like op-amp designs at low frequencies, is to do a Bode plot. You just look at the magnitude and phase, and you look for places where the loop gain is high and the phase shift is 180 because you'll get a constructive feedback on the input. Alternatively, you can look at what's called the Nyquist plot. You can plot the loop gain and you can observe encirclements around either 0 or 1, depending on if you're looking at the loop gain by itself, then you want to look at 1. Or if you're looking at the whole denominator of the transfer function, you want to look at 0. And you can count the number of encirclements and derive something. This is based on Cauchy's principal argument. You can actually derive the difference between the right half plane zeros and the right half plane poles. So really what we want to get at is the right half plane poles, but the problem with Cauchy's principle and with loop gain is that we only get the difference. So if you have 2 zeros and 2 poles, you won't see any encirclements. And that's fundamentally why loop gain is not necessarily a rigorous metric. So there's lots of different techniques to do loop gain. In one of the videos, I walk through all of these different techniques. And when you do that, you start to see that, you know, these techniques, they all have their own assumptions. They come in, which direction does the signal flow? Some loop gain techniques, in the ideal sense, right, it comes forward through the amplifier and backward through the feedback. But we've all, you know, those of us who have worked with real transistors and real circuits, we all know that like transistor has an S12 term. So certainly a signal could feed back through the amplifier as well. And certainly it could feed forward through the feedback. I mean, we build power amplifiers that are feed forward amplifiers that we specifically try to inject the signal into the forward path. So we have these different techniques, Middlebrook, which is a unilateral approach. Also, that wherever you break the loop, you've got to terminate it with something. And that can mean that based on where you break it, you can have different sensitivities. So Middlebrook is pretty good because it's insensitive to impedance. In the early 2000s, Michael Tian created a bilateral version that considers signal flow in both directions. There's also a loop gain by Hurst that I cover in the videos, and one called OSTest, which is a classic oscillator technique. That's where you use a circulator and you actually inject the signal with a circulator and observe the return. And I plotted all of these techniques. I took that circuit that I showed you in the other slide, where I just have a transistor and some other stuff, and I plotted all these techniques. And the thing to note is that they all give different results, and it can be confusing, especially some of them will disagree on whether the circuit's stable or not. So, and that's all because of these different assumptions. So to really understand, so we're left with K-factor not being rigorous. I talked about that. Loop gain, it's not rigorous. We've got assumptions. We only know the difference between the zeros and poles. There's also issues with breaking up the amplifier and feedback that I haven't talked about. But we return to these fundamental concepts. So when we search for a rigorous technique to look at stability, ultimately you come back to Heinrich Bode's work from the 1940s. And so I boiled this whole tangled web back to these two fundamental concepts. And what's interesting about the book, I highly recommend reading this book, Network Analysis and Feedback Amplifier Design. It's still totally readable and relevant today. But it actually, the loop gain stuff that I just showed you, it predates this work. It was actually developed in the 1920s by Harold Black. And so, you know, these loop gain techniques were actually around when Bode came up with these fundamental measures. And in fact, his whole reason for doing this work was to develop this general definition of feedback, because basically and I highlighted this part here in the book, the other ways are ambiguous and uncertain. These loop gain techniques have so many ambiguities and uncertainties that we can't be sure that we're actually stable. So Bode's whole goal with this work was to determine a more general definition that would allow us to have rigor that loop gain lacked. And here, by the way, here these two terms, the beta term and the other term here are the mu term are the gain and feedback terms that he's referring to. You can see them in the little feedback network there. So if you read the book, Bode basically defined two different views of a network. The right-hand side is the one that I've just covered. That's a gain feedback system. These are all vacuum tubes, by the way. And on the left-hand side, he also presented the view of a network as a set of nodal equations where you can solve for the steady state response of any of these nodes. And for each of these different views of a network, he came up with a different fundamental measure of stability. So for the nodal equations, we have driving point impedance or admittance, and for the feedback system, we have return difference. And so I just wanted to briefly go through. I put on the right-hand side of this, I put the pages from, these are actually in 2 different chapters in his book. I'm going to go the reverse order that he did and talk about them. So we'll start with the network view of gain feedback system, because I just covered that with loop gain in the last section. So return difference and return ratio, he defined these as really those ideal loop gain terms. These have parallels to the loop gain that I described, but they're done at the intrinsic ideal current source or gain element, transconductance element that's buried inside your transistor. Now this isn't, or your vacuum tube. This isn't a real thing. This is an imaginary thing. But if you go to the active source, you can actually compute this type of a loop gain around it. And even better than that, what Bode did was define it mathematically in terms of network determinants. It turns out that's actually a more useful definition than the way to do it with a circuit. So he defined it as this return difference, which is the transfer function denominator, as the determinant, the network determinant, divided by the same network determinant with the active elements removed from the matrix. And so what does this mean? Well, if you think about Cauchy's principle, and I didn't touch on it too much, but Cauchy's principle, we talk about, we only know, we're looking at encirclements that only gives us the difference between the right half plane zeros and poles, right? Well, Bode in this work, he guarantees a stable denominator. So he basically is looking at encirclements, and he's searching for, if you're looking at the denominator, you'd search for zeros. If you're looking at the transfer function, you search for poles. But he's looking for only one of those things because he zeroes out the other term. That's the key piece of this. And that's what makes it rigorous. That's why you can look at encirclements of a return difference function and know that those are the right half plane elements that you're looking for, as opposed to loop gain where you can never be sure. Similarly, he had a thing called return ratio. That's a parallel to the loop gain that we talked about earlier. The only confusing thing is that there's a negative sign underlined on the right-hand side, the negative sign, which has caused, including a lot of engineers, including myself, it has caused us lots of confusion when we're doing various derivations and plots. So we got to be careful about the negative sign. The other term that Bode coined was this driving point impedance or admittance. So if you look at a network like a series of nodes or meshes, you can come up with a set of equations that describes the steady state response. And the way you can kind of look at it is like the rest of so you have some given node on a circuit. Say there's an impedance in your circuit or whatever. The rest of the circuit can be looked at as a separate block, and it's driving that one node that you're analyzing. So maybe it stimulates it with a current, and then the node that you're looking at is going to produce a voltage in response to that stimulus. So that term is called the driving point impedance. And you can, of course, invert impedance to make admittance. That's easy. It's just 1 over the driving point impedance. And he defined it similarly with rigorous mathematical terms as the network determinant divided by the same network with determinant where you remove the node under consideration. You remove the row and the column. That's what that little KK underneath means. It means row and the column terms when the node you're analyzing are removed from the matrix. So we have a sort of a global level function start and a local function where you can analyze a node or you can analyze an entire network. That's the value of having these two different views in the first place. So I wanted to just briefly cover. I talk about this more in the videos as well. And by the way, the workspace, a lot of this stuff that I'm showing here, it's available for you to download from the YouTube channel. You can go download it and try out these simulations. So if you want to compute the return difference, it's actually pretty easy to do. I show 2 ways in the video, but the determinant-based way is to go in and you basically put these high impedance probes. So you don't want to load down the circuit. If you're dealing with a current source, you do it a little differently. But in this case, you would go in with high impedance probes, and we're going to basically derive the network, the Y matrix, across this transconductance element. And then we take the determinant of it. We can convert that in the simulation to a Y parameter. This is going to come out as an S parameter. And then we simply take the determinant of that matrix and normalize it by the determinant of the case where we turn this off. So I actually in the simulation will go in and I switch off this current source. I set it to 0. Now it doesn't need to be 0. You can set it to any constant as long as it's not an AC source, but 0 is pretty convenient. So I go in and set this thing to 0 and I can turn this element completely off. You can't do that in every device out there, so I'll talk about that a little bit later. Driving point admittance, I showed how to calculate this using determinants, but probably the most useful way to compute it is actually with this thing called an auxiliary generator. If anyone uses like the stand tool, this is kind of a similar method to observe this. The driving point impedance is the input to the stand tool. So essentially, you can drive that node with a current signal, and you observe a voltage on that node, and that will allow you to derive the driving point admittance. Now, doing it in a measurement is a lot harder. The simulation just happens to be a really convenient way to doing this in simulation. So you don't need other tools to figure out whether your response is stable or unstable. You can actually use Kurokawa's oscillation condition. Talk about that a little bit in the videos as well. Essentially, instead of looking at the impedance, you can look at the admittance. So you invert the impedance. And the reason you invert the impedance is because it's much easier to detect 0 than it is to detect infinity. That's really what you're looking for, that case where the impedance is infinite and it's either it's not responding or it's acting like a generator. So you can find that in Kurokawa's case. And we look at both the real and imaginary parts to find Kurokawa's oscillate. This is a classic oscillator condition. So the real part is less than or equal to 0, and the imaginary part is equal to 0, crossing it positively with respect to frequency. So there's a little bit there to unpack, but the way I tend to think about it, it may be an oversimplification the way I think about it, but I think about it like, well, if you have stored energy, you can't be certain that there's an oscillation starting up. So what we're really talking about with Kurokawa's condition is an autonomous oscillation. That's important. An oscillation that will just start up by itself. It doesn't need any external stimulus to start it up. Okay, I'm going to move on now to some modern extensions of Bode's work. So Bode's work was done in the 1940s. It's based on like one vacuum tube, right? So today, if you have a circuit, usually you've got multiple active sources. In fact, in your transistors, you probably have multiple transistor models. You have multiple active sources, and then you have multiple transistors in a modern circuit. So Wayne Struble and Ariel Plasker came up with this extension of Bode's original return ratio concept to allow it to account for multiple sources. Basically, he showed that you can set all of these, and what you need to do is expand the matrix to account for these sources. And they were basically able to show that you can do this one at a time as a return ratio, but you can also sort of do it all at the same time if you set everything constant. Because if you set all of your sources to a constant, if you have n sources in the network, then the denominator will still be stable for that overall function. So I made a little more of a complex. If you have one active device, the normalized determinant and the return ratio are the same. Essentially the same thing. So I made 2 transistors. I made an amplifier with 2 different transistors, and I had a feedback block. And I'm not sure how well hopefully you can see it on the slides, but I actually went into those transconductances and I applied the high impedance terminations to all of those 4 terminals of the transconductance. And then, before I had a 4x4 matrix, because now I have 8 terminals because there's 2 transistors, but I did the exact same procedure. I just swept them, turned them on, turned them off, computed the network determinant, and that's the normalized determinant function. And I'm observing the encirclements of the origin for the normalized determinant function. So if you're using ADS, you can do it in like 4 equations or less to get the normalized determinant function. There's another method that I wanted to talk about. I haven't covered this too much in a lot of my prior presentations, but this is something I've sort of recently been introduced to by Dr. Winslow, and it's kind of an exciting thing. Which is this concept of network bifurcation. So, again, it's all about getting a stable piece of the network that we can analyze. And so there was a paper. A lot of people, haven't read it because it can be a little tedious to implement the method. But essentially, it was a paper by Ohtomo. I've got the reference. You can bifurcate a circuit into active and passive blocks, and as long as each of the 2 blocks is individually stable. Now, if you're using a crazy, 200 finger FET that's just massive, then it's probably not a great assumption. But if you're using FETs from well-known vendors that are relatively well-behaved, if you bifurcate at the device input, that's a fairly safe assumption. Then you don't need to go into the current generator. You can actually just apply the bifurcation externally without losing any of the rigor. And essentially what you do is you observe all of these interface nodes and you successively inject a signal through a circulator into each interface node. And you do it in an iterative manner. So you put isolators on some of the other nodes as you walk through it. And you compute a family of loop gain, essentially loop gain curves. And when you observe the encirclements of those loop gain curves, it turns out that you can get a global rigorous analysis of stability similar to normalized determinant without needing to go through into the internal device and turn everything off. So this is the same circuit I showed for normalized determinant function. And so how do you compute Ohtomo's loop gain on this type of a circuit? Well, I would, of course, bifurcate the active devices. This is one of the S blocks, and everything else is passive. So that's the passive block. So the red is active, blue is passive. And then there's 4 interconnects in this case. This is sort of an idealized case, but there's 4 different interconnects here. And I walk through, so I basically create 4 different copies of the circuit. Or I can run 4 different simulations too, that's fine. And I start here, I put a circulator with termination in here, and I inject the signal in, and I observe the response at the other side of the circulator. Then I move to the second node. I replace that original circulator with an isolator on the input port. I inject the signal, do the same thing. I go to the third node. I replace those 2 with isolators pointing back at the devices, et cetera. And I compute 4 different loop gains, which I can observe an encirclement then of the 1-0 term because it's a loop gain. So I've got 4. I showed you a couple different techniques here. Common techniques like loop gain and K-factor are useful, but they're not super rigorous. Rigorous stability analysis, I showed you that in this section. You can do it like this. You can compute driving point admittance, but it's only going to apply to the node you're currently analyzing. So if you have 100 nodes, and you're looking at one, you can determine if that node's stable, but not if everything's stable. Internally referenced, that's pretty important. Return ratio or normalized determinant function can give you a global, rigorous view of stability, but you must, for normalized determinant and return ratio, you need to be able to either access the internal generator or at the very least be able to turn it off, which with Foundry models can be pretty challenging. Network bifurcation with Ohtomo's method is good, but the individual blocks must be stable. Also, you probably could get a feel for when I showed you that technique. It's awfully tedious in a real-life circuit. You might have 100 interface nodes in a real-life circuit. Then you have to repeat that process, that iterative process 100 times, which frankly is why not a lot of people use it or have heard of it before. So when you look at all these techniques, you kind of are left with pros and cons for everyone. Like there's no clear technique that's perfect in every scenario. So I'd like to offer a more practical suggestion here, which is why do you need to use one technique? Actually, I'm going to show you in some of the demos, these techniques are pretty useful when you use them in combination because it's kind of like different ways of looking at the same problem. Sometimes I think about it like plumbing. If you've got a plumbing leak or something, you don't just go into the, under your sink with like a screwdriver. You need tools. You need a toolbox. And if you've got a flashlight and if you have set of wrenches, these are all good things to help you solve a problem. And that's the same way with these stability analysis tools. So they can be quite complementary when used together. And I'll try to show you how that works. But the first problem, actually, when you're trying to use all these techniques is like they're just so tedious to set up. Here is a couple of the loop gains that I haven't really covered in detail, NDF. Everything requires a completely different setup. And I think the practical reason that a lot of people haven't looked at this too much is because it's just, there's no way, no real way to do this on a circuit. You would need to generate, a massive workspace and all that. So what Tom Winslow was able to contribute was, if you look at the common theme for all of these, it really comes down to the admittance network matrix. Talk about that a little more in the videos. So Tom derived a probe that, and I want to be clear, unlike previous probes that were kind of similar to this, this probe returns bidirectional impedances and admittances which are accurate even under the presence of feedback. So some of the previous probes that were out there, like the S probe, are useful, but you'll find under feedback that they break down. They don't give accurate results. And I just showed you that stability problems arise from gain and feedback. So if you can't analyze the impedances in the presence of feedback, it's not very useful. A probe isn't very useful. So I wanted to talk a little bit now about just how does this probe work? Essentially, I have that amplifier feedback example that I've been using the whole time. I put a set of probes at the input and output, and from that, I can essentially derive all of these different stability metrics here. And it's not just the ones I'm showing, by the way. These are some ones that I've covered manually. So let me just walk through them. So we'll start out. This is an OS test loop gain, so I would insert a component. It's basically a circulator, but you can find it in any design tool. It injects a signal, observes the return. Well, for the probes, we can actually just run two sets of equations in the probe results, and we can do this on virtually apply this to any node we want. And what I'm showing here is the red curve is from this WS probe, and the blue curve is from an original simulation that I did that looks like what you see on the left. So these two are equal. You can also do this Middlebrook loop gain. The Middlebrook's loop gain has voltage and current injection, and essentially you do a bunch of equations. Well, based on the probe outputs, we can compute that with one equation. We can run a Hurst-style loop gain that bifurcates, that actually breaks the feedback and amplifier and computes two separate Y-parameter networks for those and then combines them in parallel. You can also do Tian's bilateral loop gain. Personally, I think this is the most useful loop gain because it's based on the injection, so it's not sensitive to the loop and the location in the loop, and it's also bilateral, so it considers signal flow in both directions. We can derive that directly from the probe example. We can run a normalized determinant function because we can derive a Y matrix from any number of probes in there and simply toggle the source and take the determinant. And we can also do the driving point admittance that's directly output by the probe as well. And finally, I should mention, this is new in ADS 2021. We can also do Ohtomo's bifurcation analysis. So essentially, we set up the probes to point in towards the active devices consistently. So either the gate or the generator or the load side would point into the active network, and then you essentially run the probe network through this equation, and it'll derive these Ohtomo-style family of loop gains based on all your probes. And this is just matching the result that I showed from earlier, where I bifurcated the network and I added circulators and isolators to all the nodes quite painstakingly. I can match those results by just sticking probes properly configured into that same network and running it through this set of equations. So it'll virtually bifurcate the network, it'll virtually apply the isolators and circulators and compute an accurate result for you. Finally, the analysis is trivial to extend to large signal. So basically, when you're running a harmonic balance simulation, you can double click on it. You check a box that says perform stability analysis, and you're all set. And so I'm just showing a couple. This is an example of how hard it is or how tedious it is to do a basic large signal analysis when it's easy to just do it with the probes. Okay, so my goal was to kind of just walk you briefly. I know some people have already seen the content, and I want to keep it interesting. So my goal was to kind of just walk you through at a high level these different techniques. If you didn't get everything in the last section, I kind of went through it at a high level and pretty quickly. Go watch the YouTube videos because there's tons of detail in those. I go through like a lot of the derivations on how do you do this loop gain? First you put a source in here and how exactly to do it. That's all in the videos and the workspace that I provided. But I wanted to get here because this is, at least for me, this is the most fun part, which is doing a couple of live demos, talking about some challenges that I've seen from people in the industry when they're trying to use the probes. So I thought I'd show some of that. And I also wanted to, there's been a lot of questions like, why do you need the probes if you have K-factor? So I'd show that. And then secondly, I'll show you a kind of a neat technique that I came up with to use electromagnetic analysis in a pretty interesting way to get to like visually see where your coupling is that's giving you loop problems. Okay, so I'm going to try to share my screen here, and I think my understanding is going to take a minute or two until I can actually, or the screen will actually pop up. So there might be a little bit of delay, but I'm going to bring up Advanced Design System. I'm going to start. I'll give it maybe a couple more seconds.
Yeah, it'll come up, Matt. You're doing great. And while folks, there's been some questions. I can see your screen, and there have been some questions about where some of these resources are. You can just click on the resource widget. Okay, I'll go back on mute.
All right, so this is a common question I get a lot, and I wanted to show this. So a lot of times when people are just starting out with the probes, they they're like, they have this question, they send me a question that's something like, why aren't these probes detecting this obvious case where the circuit is, unstable? And so I want to talk about that a little bit. And I think people tend to think, well, the probes aren't giving me a consistent result with K factor, when in reality they are. So I built this workspace yesterday. And so I've got a transistor. A lot of people, if you're going to validate the probe, the first thing you do, you take some transistor model, you run a bias T on it, you put a couple of the probes in, and you run like a really basic, S parameter simulation. And maybe you look at S22 or S11 versus frequency, and you say, oh my gosh, one of these S22s is positive, and everyone who I've ever met, if you're an RF engineer or microwave engineer and you see a positive S11 or S22, that's bad. I used to be an engineering manager, and I remember sitting in design reviews, and if anyone ever showed me a positive reflective S parameter, I would never let them go and do the design. So this is something that if you're an RF engineer, you just have red flags all over the place. And then so someone has this, they have a K factor analysis. They say, look, it's outside of the Smith chart. Here is this is S22. It's outside of the Smith chart for all these low frequencies. K factor is low. The stability measure is coming up in that area too. So, but now let's look at what the probes gave me. First, loop gain. So I'm looking at loop gain from the probes. There's nothing here. It's minus 300, or some people like to look at it. This is kind of the Bode plot style where you just look at dBs. Over here is the Nyquist plot, and you're looking for a response that's going to circle something, and you get nothing. There's just a dot on there. So they're kind of left scratching their head. He's like, I know that the K factor here is unstable, but this probe is showing me nothing. Well, I want to point out something that I guess it may be obvious, but I think a lot of times it gets missed, which is we're looking at loop gain from the probe. So basically, you zoom into this probe. The loop gain is essentially you inject a signal out here, it goes through the world, and something else comes back into this side. And that's what a loop gain measurement is. And when you look at a trivial circuit like this is just a transistor with bias Ts. There's no loops. You have to be able to trace a loop that goes from the output back to the input. And because we're in the simulation in this ideal case, we have blocks through the bias networks. We have this ideal triangle for ground, which I've never been able to build that in real life. And that there's just no way for the signal to couple back. So loop gain analysis is actually quite useless in this paradigm. So the second thing people may look at is driving point impedance. Driving point impedance, remember I told you, well, that's such a rigorous measure, but they look at it and they see, well, the driving point impedance, there's no Kurokawa conditions being detected from these probe driving point impedances. Therefore, this thing looks stable. And my hope is that if this happens to you, I hope you don't give up here and say, well, the probe isn't useful, because actually it's quite useful, but you have to know how to think about these different metrics. So because this was a device that I made, I can go in and share with you a little bit more information. So I actually went into the device. I've got the parasitics. Some of the parasitics here are pulled out, like this might be a package level at a device. And I was able to put probes in here as well. So I went in and put probes inside the device. And when you put probes inside the device, not surprisingly, you see a little bit better of a result. Here's some loop gains. They go up. We could probably look at these. But still, even internally, the driving point impedance is not detecting any stabilities. And in fact, if you look at this loop gain internally, you still won't see any stabilities detected by this loop, instabilities detected by this loop gain either. So the next thing I did is, because I am able to go in with this device model, is I'm going to run a normalized determinant function. So I've looked at a rigorous measure. I've looked at loop gain, and I've looked at the K factor. Now I can look at the normalized determinant function using these probes. And the way I implemented that in the model was I just made a switch. So I pass a parameter in here, and I set the beta and alpha factors based on that parameter. If it's 1, then I set them to the values that they normally are. If it's 0, I set them to 0. I turn them off. And the other thing you should know if you're attempting a normalized determinant function computation is that you need to preserve the DC condition. So I've got a DC thing on here that basically does the opposite. When this device is on, this device is off. And when it's off, this device is on. So it preserves the DC bias current. So this is the little source on toggle that I pass in. And I'm going to sweep that. I'm just going to turn it off and turn it on. And so what I can do now is look at the normalized determinant function. So we might, this is like if you're a lawyer and you appeal a case, this is like appealing your case and saying, well, wait a minute, this thing should be unstable, right? Well, we look at the normalized determinant function encirclements, and lo and behold, this amplifier still appears to be stable. And here's the gain, by the way. You can see the gain is, for the off state is off, and for the on state it's on, and the S22 in the off state is inside the Smith chart. So what I'm basically showing you is, yes, I've truly turned this device off. It really is a stable denominator here, and yet I'm not seeing the encirclements that I expect to see. Okay, so we'll appeal it again. Let's go to another case, which is a transient simulation, because I think that can shed some light on what may be going on here. So I will X out these S parameters, and I'm going to run a transient simulation and basically try to detect some of that oscillation that I thought I'd see with the positive S22 and K factor. And lo and behold, in my transient simulation, so what do? I step the input up, basically just put a step function in the input. And at the output, this is the response at the drain node. And you can see, I do have an oscillation here. I do have something ringing. But if you remember back to my slide that I talked about with the left half plane and the right half plane, you'll quickly identify that this ringing is decaying to zero. This ringing is this is an instability, but it's existing in the left half plane. So this will decay to zero. And I can also detect that, of course, in the frequency domain and show you that, it's somewhere around where that negative value was. So I want to make this point because it's really important. You could have an S11 or an S22 that's outside of the Smith chart and still technically not have a self-sustaining, self-starting oscillation. Now, I'm not sitting here telling you that it's a good idea to design that. In fact, I think it's a horrible idea to design a circuit that does this sort of thing. I'm simply pointing out that the metrics that you're deriving, that the rigorous metrics you're deriving from this probe are designed to detect self-sustained right half plane poles in your transfer function. This is not one of those poles. Technically, this circuit is stable. The rigorous metrics are right here, at least in this particular case. The K factor, if you look at K factor, if you look at the S22 and you conclude that it's unstable, you're wrong about that, at least from the sense in right half plane definition of stability. Now, ringing like this isn't good. I'm not suggesting you design an amplifier like that. Some of you, if you try to do this, you might get fired anyway if you try to design an amplifier that has this kind of ringing. But so that's really the source of the difference, the disagreement between the terms that are coming out of the probe and the K factor. And so now let me first, before I talk a little more about that disagreement, let me just add some feedback here. And so this circuit, it's not too hard to make it oscillate. So I'm going to add some feedback, and I want to go back to my original S parameter analysis. So I'll add a little bit of feedback. I think just about any feedback. Oop, I have to undo my termination here. Just about any feedback will do on this to make it unstable. And I'm going to go back to my basic stuff. So I still see that bad stuff happening at low frequencies. I see a spike at high frequencies too in these. And now if you start looking at these driving point admittances, you see, there is an oscillation detected. There is a Kurokawa's oscillation condition detected at these higher frequencies. So the reason I'm really doing this is I want to walk you back to that earlier transient simulation. I showed you a transient simulation where we essentially had a left half oscillation. And so now what I want to do is show you a transient simulation with a right half plane oscillation. So we're detecting higher frequencies. Transient, by the way, is a great way to validate instabilities. You will see instabilities with transient simulations. You have to be a little bit careful because you kind of have to know where to look. I'm changing the time scale here. I'm going from the megahertz up into the gigahertz. And so it's the time scale is a little different. Sometimes when in a transient simulation, if you have a growing oscillation, it won't converge because you have exponential growth. And at some point, oops, I'm trying to run an S parameter simulation. I thought it wasn't converging right there. At some point, it'll just won't be able to converge. So now let's look at this transient result of the right half plane pole term. Now remember that the driving point admittance is the one that told us that this right half plane pole term was there too. You can trust me that the normalized determinant function agrees it shouldn't be a surprise, but it agrees very well with the driving point admittance Kurokawa computation. And now you can see this oscillation happening. And actually, you can see both the low frequency envelope here, that's the lower frequency decaying oscillation, and the higher frequency sustained oscillation. In fact, if you continue to walk this out, this oscillation will continue to grow. And in the frequency domain, we can look over here and see that, yes, this is at just about exactly the same frequency in the drain that the driving point admittance computation predicted that it would be. So these metrics aren't wrong. They're just giving you different types of information. So if you didn't give up on the metric, you've learned something then. You've actually learned a pretty interesting thing, which is that for this configuration with these loads, I'll remove the feedback now, this circuit is technically stable. Now, the other thing that people point out with K-factor, and that is true, is K-factor sort of covers the entire Smith chart. So there's nothing here just because you have a negative or a low value in this K-factor. It doesn't say that your circuit will absolutely oscillate. And that's the point I'm trying to make. But it's a coverage of the Smith chart. So we did the driving point admittance analysis. We did it under these single termination conditions. We did not, in fact, when we were looking at NDF and driving point admittance, look at the entire Smith chart. And K-factor covers the entire Smith chart, if you remember from school. So one thing that I wanted to show is, like, how do you deal with that? And something that you'll see designers do pretty often, if they're designing these amplifiers, is what's called envelope analysis. Particularly with like cellular PAs. I remember when designing cellular power amplifiers, these specs go back to the days when people used to pull out the antenna from the, you can extend the antenna out of your phone, and if someone broke it off, then the power amplifier would see like a 20-to-1 Viswar. And so we're very used to, in the cellular space, and load pulling the outside of the Smith chart to make sure that your circuit is stable under all those conditions. And that's really what an envelope type of analysis does. So some people have developed different loop gain envelope techniques where you compute loop gain. Problem with loop gain is like I said, if you're in the wrong place, you won't see anything. You won't see any instability. And some of the loop gain techniques are quite crude. So what I can do using the probes, though, and this is something relatively new, is I can virtually derive an envelope. I can virtually load pull this because I have the Y matrix and generate a synthetic set of driving point impedance curves, and then I can analyze all of those curves. Again, this is a rigorous metric. It goes back to Bode. I can analyze all those curves and determine if any of those curves meet the Kurokawa condition. So I've got a function here to do that. It's called H0 envelope. And I'm going to use 3 probes. Basically, this is the input termination probe. So this is like the source, gamma S. Over here, the drain, that's gamma L, that's the load. And inside the device, I have probes. I can pick any probe in this device. So with those 3 inputs to the equation, I can compute the driving point admittance. And then I just pass these loads in. So I'm computing this driving point admittance envelope. And from the driving point admittance envelope, what I'm actually going to do, so it's running through, I think I have a bunch of curves. It's running through this family of curves, and it's identifying 2 of these curves inside of the Smith chart, which are unstable. And just to verify that, I suppose I could go back and change the load. But the point I'm making here is that if you're looking at K-factor, this actually doesn't disagree with K-factor at all. K-factor never said that at 50 ohms or 100 ohm ideal termination, this circuit would be unstable. The K-factor implies over the entire Smith chart that there could be areas where your circuit is potentially unstable, and that's a very important distinction to point out. So I thought I'd go through and I'll try to type in this load manually if I can remember it, 8.7 and J120. Okay, so let's go here and type 8.7 plus J times 120 ohms. And when I run this, I'm really just trying to prove to you that even though I synthetically derived that using the probes, if I go back to the original S parameter simulation, voila, we see driving point Kurokawa driving point admittance terms. That's what these mean. These are the frequencies that are unstable. So the probe was able to predict, without actually load pulling the circuit, or source pulling for that matter, the Kurokawa oscillations. Okay, so that's my first demo. The second demo I have is, and I'm going to have a little bit, this will be a little bit more brief, mainly because I've shown this in the YouTube video. And I think that you can go watch the YouTube video on the channel if you want more information. But essentially, what I want to show here is I think is a pretty novel technique. I haven't seen anyone else show this technique before, to combine the probe metrics that we have with EM analysis to find the source of instabilities. So I've got this gallium nitride a power amplifier here. This is based on a device from Corvo and a monolithics model. I can't go in and do a normalized determinant in the monolithics model because I can't turn off the source. That's extremely common. And basically, what do I do? I build an EM structure. So I built an EM structure, and I ran, I put the EM in, and I found that the circuit was unstable with that EM. So let me see if I can find what happened. So first, I look at the K factor. I see some potential problem areas. I'm looking at the Ohtomo loop gain now. So now, before I couldn't really have a global, rigorous analysis of the stability of the network if I didn't have access to the intrinsics. But now with Ohtomo's method, the bifurcation method, I can go in and look at that, and it shows that this is unstable. Driving point admittance on the gate and drain nodes shows a set of oscillations, one below the carrier frequency, this is at 1 gigahertz, and another above the carrier frequency. And you can start analyzing the loop gain. You see there's gain spikes in this area. You can analyze it forward, backwards. You can figure out which direction from these loop gains the signal's flowing. This is kind of a trivial example, but it's flowing from the drain, of course, to the gate. But in other cases, you may find that the signal is traveling in the opposite direction. So you can detect with this method sort of feed forward oscillations. Okay, so in the analysis, essentially what I do is I take this circuit, this unstable circuit, and I do it a little different simulation. Instead of a harmonic balance simulation, I run an AC simulation. So I just ring this circuit with an AC signal at the input and just hit all the nodes with some kind of voltage. And I'm hoping that at all the frequencies, enough signal leaks through. Most of it bounces off the input, but I'm hoping that at some frequencies, some of this signal will get in here and stimulate for me a similar oscillation condition. So let's see if I can find my unstable. So here's my layout. And from my layout, I can launch our EM tool in Advanced Design System, which is called RF Pro. So RF Pro will snapshot my layout, and it's going to allow me to perform the EM analysis. So I performed an EM analysis on this entire board. It's a pretty simple board here. But now what I can do in RF Pro is I can actually go in and start looking at some current densities in RF Pro. So I'm going to plot here the near field result. I'll turn off these arrows because I think it looks a little nicer. It's easier to see. And so I can stimulate any one of these ports that I have. But the more interesting thing, I think, is that I can use that AC analysis that I did and excite the circuit. And that's pretty cool because now I can look, with my, let's see. So here I did this AC sweep. I did it this morning. It's pretty quick analysis. And now what I'm seeing is the way that the circuit itself is actually exciting the physical EM structure. I'm going to change the scale a little bit. So I'm down here. Well, first of all, let's go up to the transmit frequency. So this is 1 gigahertz. So the transmit frequency, these are DC terms. They're blocking the signal. And here's the AC, and everything is going through the amplifier. So that's cool. Down at low frequencies, remember there was a low frequency oscillation. We saw it in our Kurokawa oscillation condition. You can see where the board lights up. This is actually the bias line ground. So my bypassing ground signals coupling through here. If I need to separate these two bias lines from each other, and that's going to improve the stability of the system. Go up above the transmit frequency. It's not coupling now anymore through the bias line. The coupling that I'm experiencing that's causing my instability is very clear here. It's coming through the ground from the output to the input. So 2 different oscillations and 2 different causes for the oscillation. And with this type of EM and circuit co-analysis, you can very easily, very quickly get to the bottom of these kinds of problems. Okay, so those were my 2 demos for today. I'm going to stop sharing and hopefully come back to the media player here. I just want to give a closing slide and we could take some Q&A. So hopefully I've showed you that this Winslow probe is a new way to simplify stability analysis. I really hope if you want to learn more, go watch the YouTube series and definitely download the workspace. I got a whole bunch of papers. If you want to read a lot of papers on stability, here you go. These are in. I'm not going to stay on this for too long. These are these are in the presentation you're going to get. So I think at that point we've got a few minutes for questions, Carmina.
Yeah, we do. And before we get to the question, so you actually have a lot of questions from anywhere. Who were your professors were? What's the difference between, the S probe and WS probe, and a little bit about subharmonic stability as well. So, folks, we have folks like Matt here that can help you. If you want a technical expert to contact you, if you want a demo, if you want a quote, or if you want further training, you can also reach out to our Keysight sales folks and our application engineers. We're all here. So thanks very much. Don't forget to fill out the survey. You have a chance to win one of 2 Amazon.com gift cards. And let Matt know how he did. I thought he did pretty good, pretty good. So, okay, Matt. So, Matt, you have a lot of questions, and we'll try to get to some. So here is a question from Nathan. He asked, can the WS probe completely replace the legacy WS probe?
Legacy S probe, I assume you mean. Yes. So essentially, what he's referring to is there's an old probe that's been around for a while that goes back to Campbell and Brown. This classic analysis. There's great white papers on it, and it's this S probe. And so this S probe is something that is in all the design tools. And yes, the WS probe is really not like a completely new concept. The WS probe is an adjustment of that original S probe to make it accurate in the presence of arbitrary feedback. So yes, it will give you, for cases where there's no feedback, you'll get an answer that's exactly the same as the S probe. But, and I show an example in one of the videos in the workspace. You can go see it for yourself. If you put some feedback around the S probe, you start to see results that get to be nonsense. And when you look at the WS probe under the same conditions, those results are accurate, and that's why we can use it so accurately for stability as opposed to the previous S probe. So the short answer is yes, you can replace it.
Okay, good. And here's a question. I'm not sure if you have enough time to talk about this one. Sharir asked, would you talk a bit about subharmonic stability? Is there any way to simulate that?
Yeah, the probes can detect subharmonic oscillations. I can probably provide, I'm looking at the time, I think I could probably talk about this for like a half an hour, but the short answer is yes, you can detect a more detailed answer on exactly how to do that. The most common subharmonic oscillation is like a diode will produce half harmonic term typically. So there are ways to do it. And remember, I mean, it's not that the probe itself is just giving you access to stability analysis techniques. So it's not really, to me, it's not like, does the probe do or not do something? It's really like, does the technique itself detect the oscillation? And yeah, short answer is yes, there are techniques to detect that.
And here's a question from George. Is there a video or webinar that uses the WS analysis, but for an oscillator design, specifically in terms of integrated ASIC, LC, and CMOS or similar?
Yeah, I mean, of course, this stuff could apply directly. I don't know if there's, well, I haven't made a webinar about it. I don't know if like Andy Howard might make a, he's an oscillator designer. I'm an amplifier designer. He's an oscillator designer. So I try to make amplifiers that don't oscillate, and he tries to make oscillators that don't amplify. But yeah, so yeah, you can, of course, these techniques, in fact, like the os test you're probably familiar with, that is an old school oscillator design technique. I'm not aware of any webinars on that, but certainly the techniques are completely applicable to both cases. Yeah, oscillators and amplifiers.
Yeah, and so folks, we do have a lot more questions, and we really appreciate them. We will need to, Matt, I know, like you said, you can spend a half hour on some of these questions, so we'll have to take them offline. You promised to answer them via email, right?
I enjoy it, yeah. I'll have it, my cup of coffee and go through the questions, and I'll make sure to answer everybody's question.
Yeah, and also Matt is preparing for his next webinar, which is designing wafer level chip scale packaging, which is coming later this month. It's like it's a bonus October month from Matt. Yeah, so Matt, thank you so much for presenting today. Always a pleasure.
Sure, happy to.
Yeah. So thanks everyone for attending. Don't forget to fill out that survey. Let us know how we did. Let us know how we can help you. We are here to help you. So don't forget that the slides are ready. You can download some of the workspaces that he mentioned. Some may need a login. We have the playlists on YouTube, which will lead you to more awesome ESOP EDA YouTubes or Keysight YouTube videos. So again, thanks for attending today's Everything High Frequency Circuit Designers Need to Know About Stability Analysis. Now you know. And brought to you by Keysight Technologies. please visit us at www.keysight.com/find/events. And stay well, be good. Bye, everyone.